mechanical vibration. The objective, the main objective, is that basically to study the behavior, or we call that response, of a system. A system means anything, a structure, mechanical system, aerospace structure, doesn't matter. Nature makes, object, whatever that is. So we want to study the behavior or the response of a system under the action of undesirable, time-dependent, disturbances. I made it more difficult, or sound more difficult than it should be, right? In the language of human beings, what it means that we want to study if a force that is time-dependent acts on a structure or physical system, how that system responds, or how do we analyze the behavior of that structure under the action of a time-dependent force or displacement, or in general, disturbance, environmental effect. That is the main objective, So to start with that, as I said last time, this can be schematically described by this system diagram. Basically, you have a force or a disturbance, because this can be displacement, acceleration, whatever. Let's say for the time being, assuming we have a force acting on a system, and then we have a response or the behavior that as a result of the action of the force results from this system. So there are three components involved, right? In other words, this is now translated to this diagram, and it comes down to three components, right? Each of which we want to spend first some time to understand what it is. Because it's a little bit more maybe complicated than, for instance, statics or even dynamics. Because in both cases, their system was not that important. It was mainly the force and the outcome. In statics, we emphasize on understanding the force, or how to model a force, vector, equation, and how they add up, rotational versus translational effect, and so on and so forth. What it is really important is really the heart of this course is understanding this. But nevertheless, let's go one by one. So we have a force, This is the external source of disturbance, and it is usually undesirable. It is time dependent. So at least compared with statics, the forces that we are dealing with here are time dependent. As far as the response goes, so I don't go exactly with that order, we know, at least this is to some extent like statics or dynamics, that when you have a force acting on a system, the outcome is something that is also, it basically is what we are interested in, and its outcome is usually a displacement or some functions of the displacement. Can be velocity, can be acceleration, or can be a force, So definitely this is something that we really want to find out. In other words, we do need to find out when the force acts on the system, what happens. That's the main objective. However, the linkage between the two, which is very important, is the system itself. System, as we basically will see, can be described as the linkage or the bridge between the real world and basically the world we call the analytical world. What does that mean? That means in any course, not just even vibration, in order to study this, understand this, we need to come up with a mathematical model. That's what the system is. That will enable us to study it, understand it, find out basically about its behavior, and so on. So we are dealing with these three components. So let's, one by one, start, talking about each of these components, okay? As I said, of course, the most important one is the system, that we're going to spend quite some time to discuss that, okay? So, what is a system? When we talk about a physical structure that is acted upon by a force, right, as we did in the statics or dynamics, of course, in those two courses, we did not fully describe, neither were we interested in understanding what happens if a physical structure is acted upon by a force. Now we are going to spend more time and really understand it here, because that is really the building block of everything we do in mechanical vibration. So what is a system? I said the system is the sort of a bridge between the real world and the analytical world. What does that mean? That means this. If you have a structure that a force acts on that, or environmental effects basically act on that, okay, what happens? Or what are the attributes? What are those key characteristics that can fully describe a system? In order to model a system, we really need to know what a system is. To know what the system is, we need to know what are the fundamental characteristics, the attribute, the essential elements that can fully describe everything we want to know about a system. We know one thing, at least, from dynamics, and that is any system in the world has a very important attribute or inherent characteristic, which is called mass or inertia. Okay? So mass, slightly different from inertia, we'll discuss that, but mass is one of the key characteristics. And usually what happens when we say this force acts on the system, force is really acting on the mass, the inertia of the system, and as a result of acting on that, moves that, right? So when the mass or the system is subjected to a motion that takes place, and we'll talk about, of course, the motions as as we were talking about, the first thing that system does is start resisting that action, resisting the action that the force wants to impose on it. Okay? So the force wants to move this mass, and what does that mass or that system does? Resist the motion in two very distinct ways. Okay? Resists deformation. That's the first thing that system does. It tries not to bend, not to basically allow the force to make any changes in the characteristics, in the sort of the physical shape of the system. In other words, resist deformation, right? So what is that ability that resists the deformation? You've seen that in strength of material. we call that elasticity. So that's one of the characteristics you didn't care about in dynamics, but you studied that in strength of material. What you didn't study in none of those courses was that there is also another way that a system resists motion or deformation and not allowing the force to change it. What is that attribute? It's an attribute that cannot be physically in a very straightforward way, like elasticity, be described because it's a very, very complex phenomenon. But what that characteristics is resisting the motion by absorbing the energy that motion is going to inject in the system. So we call that energy absorption. Any system in the world, as long as you can identify these three inherent characteristics of, can be easily modeled in form of a mathematical system. So the challenge or the important task in this course to understand a system is, and the first and foremost task we want to tackle is how to identify these three elements in any physical system so that we can actually model that and then deal with that. In order to do that, we'll get back to this. In order to do that, first of all, we need to make, like anything else, some assumptions, or different terminology for that would be idealizations, or which is a different way of expressing assumptions. Okay? So in order to really understand the system, mathematically model that, let's say make some idealization. First of all, as far as the motion itself, we say the whole course is about motion, forces causing the motion of a physical system. The types of motion that we are dealing with are no more than two. One is called translational. The other one is rotational. These are the two types of motion that we will be dealing with in mechanical vibrations. What is the difference between the two? Does anybody remember from dynamics what is the main difference, or what is it that differentiates this type of motion from this type of motion? Anybody? In translational motion, okay, what we are dealing with a mass that is moving in one basically linear translational direction. So all we care about is that what is that mass, right? And our focus is on just the center of that mass. It is the center of that mass that moves along a line, right? And that's what basically we are dealing with. We have an inertia moving along a line. That describes the translational motion. So what the shape of it is, how the mass distribution is, doesn't matter. As long as you know where the center of the mass is, we assume that all the mass is basically lumped at that location, and that's all we care about. In the rotational motion, in other words, let's say distribution, not important. On the other hand, in the rotational motion, what really matters is the distribution, or how that mass is distributed about the center of mass. What do we call that? Distribution of mass about the mass center. Mass moment of inertia, right? So in the rotational motion, it is the mass moment of inertia, not the inertia itself, that comes into picture. And as you remember, of course, the formulation of the equation of motion in dynamics, you've seen that. So that's the first idealization, that we're dealing with these two motions and what each of these basically limitations or idealizations basically translate into. The second thing that we need to discuss is talking about going back to the system itself. So again, let's go back to the system. A system consists of a lot of mass distributed throughout the whole structure, right? So when any physical system moves, whether take it is a natural structure, a tree, or an animal or human body or whatever it is, right? Or a physical structure, a building, a light pole, or a car, every single piece of that mass experiences a motion, right? Each motion that takes place in whatever direction is called a degree of freedom. In other words, every single piece of mass in a system moves in certain directions, which we call that degree of freedom. So in general, any structure in general has infinite number of degrees of freedom, right? So that's not a very easy and fun way to deal with the inertia or the mass in a structure. So in order to make the life, again, easier for us, we make another idealization. And the idealization is based on this. Think of it this way. Let me sort of give you an example that makes understanding of this concept better. If you have, let's say, a water tower, okay, or a tree, or a light pole, it doesn't matter. If this moves, right, and you have an intuitive way of estimating or having a good understanding of some overwhelming fundamental motion that this goes through, what it looks like, right, then you can actually idealize this infinite number of degrees of freedom to a single one. How does that work? If this thing deforms, what do you think is going to happen? It's going to move like this, right? Or a tree usually moves like this. Does it remind you of something? A cantilever beam, right? So if this thing is moving like a cantilever beam, right? Cantilever beam usually moves this way due to the action of a single force at the tip of this, right? So is it reasonable that we assume that since this has a mass and it is moving, the reason it is moving this way is a dominant inertia of this system is basically right here, and it is moving this way. And as long as I have any information about the motion of the mass at this tip, I can relate the motion at every single point along this structure to that, right? This is a well-defined mathematical curve. So if I have this delta, I can relate every basic displacement along this beam to this. So let me rephrase it in a different way. If you can identify, okay, what we call a single independent degree of freedom that can describe the overall motion of a system, we call that a single degree of freedom representation of that system. So a single degree of freedom means assuming that the entire structure is basically can be represented by its total mass. You know how that total mass moves. Overall, you have an overall sort of understanding how that moves. And the movement that this goes through, we call that the degree of freedom. So with that said, now let's go back and see how we can put all of these that I've said together in a meaningful way that really lays the foundation or the first building block for studying mechanical vibration. So what is it that I have said? Now, I said that any physical system, right, consists of three inherent characteristics: mass, elasticity, energy absorption. But it comes down to the fact that if a system goes through motion, and motion described as a direct, translational or rotational, what is actually moving is that single mass. But motion of that single mass, which is subjected to the applied force, which is causing it to move, is resisted by two components that resist that motion: elasticity and energy absorption. So how about this now? As long as I can identify that single mass in a structure and that single degree of freedom, okay, that's the question mark for the time being. As long as I can identify that, is it allowable, do you allow me to say that, okay, any structure can be just thought of it just a piece of lumped mass, M, subjected to a force, okay, whose motion is resisted by two inherent forces. One is a force that, if you assume this is linear or translational motion, is a force that resisting the motion in that direction. Think about this. Again, going to that cantilever beam. This cantilever beam, right, is moving in this direction, in translational direction. What is resisting it is the stiffness or the spring that this beam represents that is resisting that motion, right? So the spring, in a way, is subjected to that force that is applied to that mass, right? It is that, in other words, this spring is subjected to a one-dimensional force acting along the direction of that flexible element. Does that remind you of something? In the strength of material, you have a force that is acting along a bar, and that's all that does, right? So that represents a spring, right? So this force is nothing but what we call a spring or stiffness element that is resisting that motion. Okay, that's what we refer to as the force that resists deformation. Deformation takes place in only one direction, so this is like a spring. There's another force that is also resisting that motion. And that force, we call that energy absorption force. This force is easy to describe. This mass goes through a deformation U, so goes from here to here, right? So if this moves in that direction, this element resisting the motion also in that direction, assuming that it's linear, so the force that is generated here, which I call that F of K, would be just the stiffness times that displacement. That is that force. How about this guy? This one, anybody knows how we deal with this one, or what we call that? We call that energy absorption unit, or a damping unit. And in order to represent this force, we just simply fudge it, because we cannot fully mathematically describe it in a simple way. So we describe this based on a very, very simple and rough assumption. And that assumption is that this force, which we call that a damping force, is proportional to the velocity that this mass experiences. A constant that we call that a damping coefficient times the velocity. Don't ask me why, it's just an assumption. It's not a good assumption, but it's a working assumption. Okay? And obviously as this thing moves, right, it is going to generate or go through some displacement. So now let's see what happened here. It's wonderful. This is the better representation of what we had here. We said vibration is studying the effect of a time-dependent force on a system and trying to find the response. Now, with what we have set up here, okay, we now have been able to convert this to actually an idealized mathematical model that has all the information contained in this diagram. How? The system, as we said, represents three inherent characteristics: mass, stiffness, and damping. So this diagram includes that. This diagram also has all the information we need to find about the response, as well as the input to the system. So now we've come a step forward and getting to where we want to be. And that is, we have come up now with a diagram, a schematic, mathematical representation of everything we talked about. We talked about disturbance, we talked about the system, we talked about the response, and this diagram, in a nutshell, gives us all those information. But what else it does? This is, in a way, a physical, sort of represents a physical model, right? Like a truss, like a frame, like any structure that you've dealt with. So when you're dealing with a structure like that, okay, in order to analyze this, what is the meaning of analysis? What did you do to analyze a structure in statics or a strength of material? In a strength of material, you had something like this. Not exactly like that. You idealize a structure that would go through a uniaxial deformation as something that you call that a bar, right? That modeling allowed you, by using free body diagram, to identify all the internal forces that happen in this little structure and then convert that to the intensity that you call that stresses and whatnot. You also had something else, a structure like this. You call that a shaft. So by establishing this model, you could do all kinds of wonderful things. That if you had an applied load, of course the case was time-independent load, you could find out all the forces inside the structure and the intensity of those, right? If you had something that was subjected to basically forces that cause deformation in form of bending and cutting off or the shearing off, then This was a model that you used to find the internal forces in this. But the tools that you use, including a tool that you use in static, the first fundamental tool that is the foundation of everything that you learn in static is what? The key tool to analyze this mathematical model is what? You learn that in statics. That's the only thing that I expect you to remember from statics. What was the tool? I emphasize in my course that it's 85% of statics. Free body diagram. That's what we're going to do to study this creature now. Right? That's what you did in dynamics too, I assume. Right? Okay, what does that mean? You have a system that is going through the action of an external force, right? That's one force. You free that from all the constraints. Then you put back the effect of all the forces that are acting on this structure. This is the external force. You have a force that is resisting its movement in that direction, resisting the deformation. This is experiencing a displacement, right? And another force, which we call that damping force, right? Is there any another force that I should put here? We're talking about now, not statics. To analyze a structure in motion or under the action of time-dependent load, right? We use, instead of the first law of that guy that I always hesitate even to mention his name because he was a big thief of all time, Newton, Galileo's law, which is the more correct way of describing it because he's the one who actually discovered all these. What was that? In statics, we use the first law, right? In dynamics, we use the second law, right? And what was that? However, using Newton's law or the Newtonian mechanics is not at least as easy as what I consider, in fact, using the lumber principle. I'm sure you've had that in dynamics. The lumber, Mr. De Lumber. You never heard of Mr. De Lumber? All these great mathematicians from France that have contributed so much to the world of mathematics and science. For some reason, France has given more, outstanding mathematicians to the world than any other country. I don't know if it had anything to do with the Mediterranean Sea or the weather, whatever it was. The lumber, Lagrange, who else? Laplace, you name it. But anyway, what was the lumber principle? The lumber principle says you can treat any dynamic problem as a static problem. In other words, just set up the free body diagram of the system, assuming that this is a static problem, if you add to basically the free body diagram a force which is in the opposite direction of motion, and that is the force of inertia. So then this becomes a static problem, and you can just use equations of equilibrium, okay, to set this up, to set up the mathematical equation, which becomes mu double dot plus cu dot plus ku is equal to f of t. Now look what we have done. We started with all those philosophical discussions. We came down to talking about more the schematic representation. We talked about the system and all of that, and at the end, all of this resulted in a single equation, which we call that equation of motion, and that is what is the heart of vibration. So mechanical vibrations comes down to simply two major tasks. First, we spend a few weeks addressing the first one. So, tasks or objectives. Objective number one is how to model a system or a structure as a single degree of freedom system. In other words, if you're given a mechanical system or a structural system or naturally made system, how can you identify what is this lump mass, what is this stiffness, and what is this damping element? If you can succeed with that, in other words, if you can solve that model by identifying the actual value of these in terms of the physical and geometrical components of the system, that's it. Because then you can easily set this up, right? So the second step, so we spent probably about, give or take, about 3 weeks. The second step is how to solve the equation of motion. You would say this is a piece of cake, right? Because this is just a second order, ordinary linear differential equation. You're right. Solving this is not the important part. Understanding the physical and the interpreting the meaning, physical meaning of the solution is what is important. What does that has to say about the physical characteristics of the system or the behavior of the system? So that's what we do. So for this part, so this is what we're going to talk about. For this part, we categorize what we are going to study according to this equation. This equation, okay, can take several basically forms, or can be of several possible sort of forms. Okay, f of t can be 0. That means the system can be moving without the action, without a force acting on that. A force has caused a system to vibrate. The wind had caused the vibration of that tree. The wind has stopped, but this is, or you've shaken that tree, continues to move now without the action of any force acting on that. We call that free vibration. Or this is not 0. When it is not 0, we look at, in this course, 3 types of forces that can act on a system. Either this is a harmonic force. Harmonic means a sinusoidal, a cyclic force, or a periodic force, something like this, or a general force, okay? You can have a blast load, you can have an impact load. These are all forces that are neither of the two. Of course, this force can be completely unpredictable or random also. But we don't even talk about that because random vibrations is a class in itself. Okay? There's another, I'll promise 30 seconds. Okay? Another way of categorizing what we study, and that is now by looking at the system and how we're going to treat that system. So we start actually by making the assumption first that there is no damping in the system. So system is basically made of a mass and deformation ability. We call that undamped system. And the second case is C is not 0. We call that a damped system. So we are going to look at and study free and forced vibration of undamped system. Forced vibration consisting of these three cases. Then we looked at free and forced vibration of damped systems. And that's the entire course of mechanical vibration. I told you it's easy, right? You just have to remember how to solve that problem, this equation.